Okay, so today, 5/14/2024, in case you missed this lecture, this video is for you. The law of reflection. Whatever the light angle, whatever the light comes in at, is going to be equal to the reflected angle. And so I want to show that as a quick little demonstration. So here I have a light box. And let's see. Ashlyn, I'm going to ask if you would hit those lights for me for a moment. Okay, so I'm gonna take this thing over to the camera so you guys can see this better. So this light box has 4 parallel rays coming out from it, and I want to show you this law of reflection idea. And so light, when it hits, and oftentimes we'll look at just a mirrored surface, we would say that the angle of that light, the angle that the light comes in at, is equal to the angle that it leaves at. Okay, so if I were to draw a line here, sort of bisecting that thing there, you would see that the angle at which the light ray comes in is equal to the angle at which the light ray goes out. Okay, and so parallel lines remain parallel, and we would say that that is a certain kind of reflection. Now I'm going to show you, I'll give you those terms here in a moment. If I shine this thing on the back, you can see that the light is hitting here, but it's not like maintaining its order. It sort of scatters. And so there's 2 different kinds of reflection that we want to be able to look at. One of them, it depends on the texture of that surface. So just how rough is that surface? We have something called a diffused reflection. So diffuse is to take light and sort of get it to scatter. This term, you'll see this on your quizzes and tests to see that it's diffused. The light sort of spreads out and it just reflects randomly in a variety of different directions. It occurs when surface variations are larger than the wavelength of light. So the surface is fairly smooth, but the light itself is really, really short wavelengths. So if the surface variations are larger than the wavelength of the light's going to sort of scatter. I'm going to pull this thing over so you can see it better. Roy G. Biv, we talked about the visible spectrum of light. The lowest frequency, longest wavelength is red. And so we would say that it varies between 620 to 750 nanometers. That would be in the order of 10 to the negative 7. So these are very, very tiny wavelengths. Nano means 10 to the negative 9. So these would be in the order of 10 to the negative 7 meters. Violet is the shortest wavelength, highest frequency. It goes all the way down to 380 nanometers. So very small wavelengths. Much smaller than sound. If we think about sound, audible sound range varies from about 1.7 centimeters to 17 meters of length. So these are very, very tiny. The surface has to be incredibly smooth for us to be able to see that light being reflected and maintains order. So we would call this specular reflection. Specular, you might think of that as spectacles, for those of you that wear glasses. We are able to maintain order. So the light reflects off of that surface and it still contains the same information that it had before, right? So if we think of those light rays as containing information, it could be an image of an object, that image is maintained. Okay, so we'd say that it maintains order. Now that's for reflection. Let's see, Tayden is going to be doing a speaker project on subwoofers, right? Or your project, your presentation is going to be on subwoofers. This has to do with diffraction. Now this will not, you notice an asterisk, this does not go on your quiz or exams. So this is a spreading out of a wave that's going to sort of bend around an obstacle. And we can hear or see that sound wave or that light wave on the other side of that obstacle because it sort of spreads out as it goes past that. Subwoofers, the bigger the speaker, the better the sound will diffract for low frequency waves. So Tayden, yours is you're going to be doing subwoofer stuff. This graph that I have up here is just showing how the size of the speaker is related to the size of the sound wave that you want to play. So if you're using a subwoofer, you want to have a bigger speaker cone. And so you said you have 2 subwoofers in your car. This is for playing frequencies in the 20 hertz, really low bass, all the way up to maybe around 800 hertz, somewhere in that area. Works better for low frequency, long wavelength sounds. The tweeters and the super tweeters and so forth are for higher frequency players, right? And so that again has to do with diffraction. So how much the wave sort of spreads out. Okay. The amount of diffraction is wavelength dependent. So how much diffraction you get depends largely on how big that object is in relation to the wavelength. Obstacles and openings that are comparable to the wavelengths will produce more diffraction. Again, you're not going to see this on a quiz or an exam, but this has to do with the spreading out. Now, the last topic for us to look at for today is this thing called refraction. Refraction is when we bend light, we change its direction when it passes from one medium into another. Okay, so the light ray that's coming in at an angle is going to bend as it enters a new medium. And so before we go through this here, I want to look at these things over here. If this is a wave source coming in from the left, and it approaches a medium in which the speed changes. Yep, Connor, thank you. I'll take it. You got it back. Thank you for that. Good luck to you, Connor. Thanks. Here's a slow medium, so the propagation speed is fairly small. This is a wavefront. When it enters into the fast medium, could you draw for me what you think this waveform would look like when it goes into a fast medium? Just take a moment, see if you can draw for me what it looks like as it traverses this barrier. Right. Take a moment to do that. Ryan, how are you doing? Good. Good. I got to talk to you for a second. Once you have that, see if you agree with your elbow partner on what that looks like for the slow to fast medium.
Yeah.
So, thank you, folks, for giving some patience here as students are having to take exams today. All right, so this waveform should look something like this. Apparently, I lost the ability to draw on this, so I'm going to go ahead and use this here. If it speeds up, then the wavelength should increase. I'm going to draw this with some lines here. So these things should be further apart now. Okay, let's try that again. So the wavelength should increase because the speed has increased, and so the wavelength should be bigger. Okay, does that make sense? Speeds up, it travels further in the same amount of time as it did before. Now, if I go from a fast to a slow medium, the opposite should happen. The wavelength should become smaller. And so if I were to look at this hitting that boundary straight on, then the wavelength should become closer together as they travel now at a slower speed. Now, when they enter at an angle, The amount of refraction depends on both the angle that it comes in at. So what is the angle that it hits that boundary at, and also how much the speed changes. So if the speed changes dramatically, we get a bigger amount of bending. Now I'm going to try this because I need to be able to write on the board. So I'm going to unplug this. That should allow me to get back on and be able to write on it. Please forgive the technology issues. This is going from a fast to a slow medium. So if I think of this as a fast medium over here, and this is a slow medium, these waves should sort of lag behind as they enter into this new medium. So I'm going to draw that as a waveform that sort of is falling behind. So that's going to be a little bit of a bending to this thing. And so what we notice is that the wave sort of changes it in its direction. So this wave would now sort of bend toward what we call that normal line. So if this is the direction that the wave was traveling, now it's traveling at a different angle. This angle here is what we call the incident angle. This angle here is what we call the refracted angle. And so that light's going to bend. If you ever been out looking at fish in the water and you do some spear fishing or something along those lines, you see this all the time in the movies. If you throw it where you see the object, you're going to miss it because the light bends as it goes in there. So you have to throw it at a different angle. If I go from a slow to a fast medium, now this interface will show that the light ray sort of gets ahead of this, and you'll see that the bending occurs where this thing will now bend away from the interface, and you would see that it would bend this way. Again, the angles, this would be the incident angle, and this would be the refracted angle. And you can see that depending on which way I go, from either a slow to a fast or a fast to a slow, I either bend toward or away from the normal one. Now again, I want to demonstrate that. I want to show you what that will look like using this light box again. I'm going to put a single slit through this so you can see this this work a little bit better. Okay, so you should be able to see that beam of light traveling across that surface. If I have that object hit that light or hit that medium at a straight on, it just goes right through it. But if I have it hit it at an angle, you should be able to see that light sort of bends at the interface. And so the light coming in hits that interface, bends a little bit, and then comes and bends again. Okay, and so how much it bends depends on what the angle is coming in and the difference in those speeds. And so you should be able to see that is changing the direction of that light. It might be easier to see if I have that light brighter. Okay. Now this is just a plain mirror or plain glass, if you will. So light is refracted a little bit through that plain glass. I want to show you, for those of you that have glasses, you can see that I can use refraction to create sort of a focusing effect. I'm going to do that using these three rays. So those rays can be focused using lenses. And so these lenses work on the process of refraction. So the light is hitting this interface, it causes it to sort of bend towards the normal, and we can see that that light is sort of focused at that particular point. So we would say that this is a lens. This is a converging lens. For those of you that can see close but not far, oftentimes you use a diverging lens to be able to create a different kind of image. So what a diverging lens does is it sort of spreads that light out. Okay, so optical instruments, whether or not it's your eye or it's a telescope or a microscope, those things are used based on laws of refraction. Okay. Questions for me? Okay. I can use combinations of lenses, and so what I have here is a diverging and a converging lens that are working in succession to be able to create some optical instruments there. Okay. So again, we don't have a whole lot of time to explore applications of refraction, but it's based on the light changing speeds as it goes through those different media. That's what I wanted to look at today, was to go through the idea of refraction. I'm going to do total internal reflection tomorrow, and so we'll look at that as our final activity for this unit. I'm going to stop the recording, and the remainder of time today, I'd like you to be able to spend some time looking at this